think about a spherical shell, okay, or a surface which is actually equidistant from the charge q. So let's say the outermost ring, what you can see, the outermost surface we are talking about, and this is r distance away from the charge. And then we have learned that exactly at this point, if we want to find the potential, then that is V is equal to 1 upon 4 pi epsilon naught Q upon R. If we go in any direction, okay, any side, the distance from the charge will remain Q, because that is the radius of your sphere. So at all these points, the potential will be exactly same, okay, because Q is same, as you can see, R is same, radius any side. So it means there is a surface where the potential is equal if there is a fixed charge inside that surface, and this we called an equipotential surface. So an equipotential surface is a surface with a constant value of potential at all the points on the surface. And what it shows, as I told you, that if V is constant, if R is constant. If R is fixed, then V will be constant. Thus, equipotential surface of a single point charge are concentric spherical surfaces centered at the charge. Alright, centered at the charge. So charge is the center. So we talked about equipotential surface of the outermost ring, but it is not fixed. If you want another equipotential surface, the inner ring also plays as an equipotential surface, because the distance from the center where the charge is, that distance is fixed. And that will give the same potential on the surface anywhere we go around it. And also you need to know that the equipotential surface makes a 90-degree angle with the electric field. So this is the direction of electric field. If our source charge is here, so it is radially outward, electric field is radially outward. And if we draw the equipotential surface, which is a fixed distance away from the charge, then this angle is always 90 degree from the electric field. So we can say that for any charge configuration, equipotential surface through a point is normal to the electric field at that point. Okay. Keep in mind the equipotential surface, how it looks like of an electric dipole, where there is one negative charge and one positive charge. So the equipotential surface would be something like this. And if there are two similar kind of charge, like positive, negative, then this is the equipotential surface. So wherever you go on this surface, the potential would be the same. Okay. All right. And in the case of dipole, it is considered that there are two charges, so two set of surfaces are built, and on those surfaces the potential would be the same. But as you can see closely that on one side, on one side you can see there is more space here, and other side is less space. The same when we go to the positive charge, here the space is less, and this side the space is more. So this you have to keep in mind. For dipole, the equipotential surface looks like this, the elongated version of it, like between the charges the surfaces are less thicker than that of far from the two charges, okay, the other side of the charges. So but for the concentric, like if there is single point charge, then it is equidistant, okay, equidistance. But since we included two charges. In the case of electric dipole, it looks different. And for equal charges, we see the thickness increases in between the charges. Okay, and all these things you just have to keep in mind how it looks like, how the equipotential surface would look like in case of different set of charges. Now the last thing about equipotential surface here is that if there is an equipotential surface, then for example this is V1 potential here, V2 potential here, okay, then there is a charge at the center. All right, so if work done in bringing a charge from infinity to a point here, right here at V1, where we have the value V1, that work done is suppose W1, okay, and work done to bring the charge from infinity to the point where the potential is V2, it is suppose that is W2, okay. And we know that potential 1 is actually work done divided by the unit charge, okay, unit charge, that is 1 coulomb, or the test charge we brought from the infinity to this point. And the same goes for V2, that is W2 by unit charge, okay. So then we can say that W1 by 1 coulomb minus W2 by 1 coulomb is actually equal to V1 minus V2, change of potential, and change of potential is delta V, okay, and our work done difference will be delta W by 1 coulomb, or let's say it is delta W now. And we know that on the equipotential surface the potentials are same, so V1 is equal to V2, that's why this is 0, okay, and that suggests that delta W is actually equal to 0, okay, which means on the equipotential surface the work done is 0 in moving the charge from one point to another point on the equipotential surface, okay. So this is also important to understand. Though whole of this practice what I have done here, it is just a way of showing you that work done on the equipotential surface is 0, but this is nowhere written in your book, okay. So this is not a very proper way to arrive at this, but just for your understanding that on the equipotential surface the work done is 0. And precisely if I talk about this quantity here, actually we are talking about work done is from bringing the work done is actually bringing the charge from infinity to the point, okay. So let's say that some work done is done here, some work done is done here to bring it from infinity to that, and that portion we ignore, and what work done we focus here, delta W, is the work done only working between these 2 points on the equipotential surface, okay, and that becomes equal to 0 because both the potentials on the equipotential surface is 0. So that makes us to believe that work done on the equipotential surface is also 0. Thank you. And in the next video we will be doing relation between field and potential, and then we'll start the potential energy, right? So thank you.